Welcome everybody, online and in person. So today we have Yassid Ayyad from IGFAE itself, who will talk to us about his research, and in particular about halo nuclei as open quantum systems. So please, Yassid, go ahead.
Thank you very much. So very happy to give this talk today, because what I'm going to explain, it's like a general overview of what the type of research we do on exotic nuclei that we view as an open quantum system, but also because it's kind of like a hot topic in the sense that there has been quite a lot of experimental effort ongoing right now and a lot of vivid discussions. So I also want to, I'm going to explain things from a pedagogic point of view, so I won't go into the very details of the theory. Of course, I'm not a theorist anyway, but I think that there's also a good introduction for the students for this type of research, of course. So basically, so the pointer doesn't work now. Okay, okay, it's blocked.
No.
Now, okay, so no, that was not the introduction here. Sorry, it was like delayed. So I'm going to talk about nuclei as exotic nuclei, or nuclei in general as open quantum system. I will give a very brief explanation of what this is, what this means. And also I will talk about, in particular, halo nuclei and quasi-free neutrons that are existing inside the nucleus itself. And then I'll talk about a very particular system, which is Berlin 11, and we have studied different modes of decay from an open system point of view. And this particular system shows very intriguing and astonishing properties, and I'll explain that. And then I'll talk about an experiment that we performed to confirm what we were observing, and then some conclusions regarding this. So as you know, there's several interpretations regarding the way we view nuclei itself. So there's macroscopic models for the nucleus, but we know that nuclei are they are entities that live in the quantum world, and they are described by quantum physics, many body quantum physics, because eventually, from a microscopic point of view, we see them as like an ensemble of nucleons that interact. So, okay. The thing is that within the physics domain, this is not an isolated phenomenon, in the sense that there's a lot of environment where the properties of the nuclei matter, in the sense that the interaction between the components of the nucleus, it's like the building blocks from degrees of freedom, from, let's say, basic degrees of freedom to complexity. And at the same time, we see that in different type of research, like could be, for example, in astrophysics or particle physics, as you can see here. So it's a complex system, and there's several ways where there's a crossroad among all these disciplines here, like a strongly coupled superfluid system, phase transitional behavior, fluctuation and statistics, properties of quantum system, which is what I'm going to talk about, clustering, which is a part of the quantum systems, and also studies of neutron-rich matter in neutron star and supernovae. You know that belong from the astrophysics point of view, and also theory like nuclear matrix elements for fundamental symmetry test, and for nuclei in general, and for neutrino. So if we have in mind that there's like a quantum ladder going from the very microscopic things like could be strings to large things like could be galaxies or massive objects in the universe, nuclei are in the middle of that quantum ladder. So depending on the type of properties that you want to study in the nuclei, you need a microscope with the proper resolution. And by that, I mean that, well, of course, the nucleon is not the ultimate structure, the smallest one. So you have degrees of freedom regarding depending on the experimental proof that you need, and there's the distance scale. And we know that there's quarks inside the mesons and baryons, and there's also in low energy nuclear physics. These nuclei are described in protons and neutrons, we know that, and the current and densities, and collective modes, like could be the rotations and vibrations of the nucleus itself, of the whole. Okay. So with that in mind, a nucleus can be seen as an open quantum system. But before going into that, it's what's an open quantum system? Of course, it has a very general description in the sense it's a system, closed system that interacts with an environment. So from a very basic point of view, like a quantum mechanics point of view, this system is of course described by Hilbert space and also by the density matrices and of course a Hamiltonian. So ultimately, this is the ideal realization of a system that we could solve with the Schrödinger equation. But this is ideal, as I said. And any system is surrounded by an environment and they can interact. So there's someone called them environment, some others call it bath or reservoir, but it's the system itself, it's not isolated, that it's interacting with the environment. And this can be found in many different physics domains, optics, information processing, computing, biology, chemistry, well, all the list that you see there. So how do we envision the nucleus as a quantum system? So, well, we just have to remember how a nucleus bound. So we know that there's a potential that binds the nucleus itself, okay? And everything that this is very basic quantum physics, of course, that everything that is inside this potential can be bound, okay? So there's bound states, as you can see here, and this is the closed part of the quantum system, okay? Now, there's also a continuum part of the nucleus itself. That's everything above the threshold energy, zero energy, we know that, and we know that in that region, states are unbound, and you have two different types of region. You have narrow resonances and broad resonances when the energy is much higher, okay? There's quite a lot of examples that could be giant resonances that are because of collective movement of the nucleus itself. But if we think about what's a resonance, which is actually something that I'm going to focus on this talk, it's just a metastable state that lives for a very short period of time. And it can be seen as an interaction between the potential itself and of the nucleus, the core, and a particle that is going to interact with it. So this part here comes from the very strong residual force of the part that the potential is binding, just because we always have in mind that we have like a box and with some boundaries there, right? So once you remove the boundaries, that residual interaction is what creates the resonance itself. The resonance is not bound, and you do not, depending on the type of resonance, that if you do, for example, elastic scattering, you don't bound the nucleus itself, doesn't form the system, so it lives for a short period of time. So with this in mind, because of this interplay between the continuum and the bound part of the nucleus, we have very exotic phenomena in nuclei that manifest, especially depending on the properties of the nucleus. But when we have exotic nuclei that are weakly bound, this manifests with much more intensity, let's say like that. So we know, for example, that, well, there's halo nuclei. This is what I'm going to talk about. It's the formation of a nucleus with a very long extended tail because of some neutrons that are, or protons, there's also that are orbiting far away from the core and, well, could be forming a halo or even like a skin. There's different flavors and types, we'll see some of them. But there's also the clusterization of states Like, for example, we know carbon-12, the formation of carbon-12, that's important to understand the formation of heavier elements in the galaxy through the fusion of 3 alpha particles, or through a beryllium and an alpha particle itself. And there's also exotic phenomena near the drip line, which is the boundaries of the nuclear landscape, where we have emission of particles, which is called proton radioactivity. Okay. Now, let's focus on what a halo nucleus is. Okay, so and what is important for this study. So, as I said, you have halo nuclei when you have a long tail in the distribution of density of the nucleus itself, of the matter of the nucleus. So, as a paradigm of the halo nuclei, you have lithium-11, which has a very long extension that could be compared to a much heavier nucleus. Could be like calcium-48, or even if one wants to go to those extremes, to a lead nucleus itself. And one important concept here is that normally those nucleons are decoupled from the core itself, so we can treat them as a almost quasi-free nucleus. Okay, and they are weakly bound, so it takes very little energy to remove them and split the core. Okay, and they used to have a single particle behavior. But when we have like a neutron, and this is something that I would like to introduce here, because this halo system has you'll see that they have properties that they are not only concerning the structure of the nucleus itself, but also things like dark matter. And we'll see also that they are connected to a very general problem, which is the neutron lifetime. So we'll see that, but first, we know what a neutron is, but even though we have been studying neutrons for many, many years, we still have some questions there that are not solved, right? So we even know that neutrons have electric dipole moment. So there's experiments actually trying to lower this upper limit, okay, to understand, well, if they can be polarized or not. We also know that inside the nucleus, neutrons can form pairs, but outside the nucleus, you cannot have a bound pair of neutrons. Okay, this is something that is still a quite hot topic, which is pairing, of course. And they exist in a quasi-free mode, which is a halo itself. And something very important, we know the lifetime of because when it's not bound to the nucleus, the neutron decays, and we know the lifetime, which is about 15 minutes. But this lifetime depends on how you measure it. And this is one of the things that's still not solved. And it's one of the major question marks in the neutron physics. And there's 2 ways to measure the neutron lifetime. One is you can put neutrons inside a bottle, literally. These are called ultra-cold neutrons. They have electron volt energies. And because they elastic scatter inside the bottle, you can trap them there and you can count how many you have. Or you can have another type of measurement where you see the neutrons interacting with the system and you can count them too. So these 2 methods give different lifetimes, and we still do not know why. So there's 4 sigma of difference between both. So it's 1% of difference that people is really struggling to figure out if this is a systematic uncertainty on the experiment, or it could be because there's exotic decay mode that has not been taken into account, not detected in the in-beam experiment itself. Okay, so there's still a lot of effort here, but nuclear physics has something to say regarding this, because we have neutrons that are lightly bound into nuclei that could be treated in a way that we could investigate this, and I'll show you how. But first of all, I want to show you how you can really put neutrons inside a bottle. This is a video. You'll see okay, so with this in mind, there's another scenario for explaining why the neutron may disappear, or where there's a difference in terms of the lifetime of the neutron itself. So there was a paper several years ago by Fornal and Greenstein, where they made the hypothesis of that there might be a way that the neutron is decaying to a particle that we cannot detect. Okay, there are several cases. We don't care about this, and actually they have not been found. But in particular, you can have neutrons decaying into a dark matter particle or a dark sector if they fulfill inside the nucleus itself, if they fulfill this requirement here. And this is literally that the mass has to be of that order between this number and the mass of the neutron minus the neutron separation energy of the nucleus itself. And that's, well, not a coincidence. It's fulfilled in neutron halo nuclei because they are weakly bound. Okay, so if the neutron separation energy of the nucleus is of 1.5 MeV, this can happen. Okay, so there are several scenarios here, and as I said before, these concerns about halo nucleus itself, which remember it's an open quantum system, and among the exotic nuclei that we have here, the best candidate that was pointed out by Fussner and Riesager, beryllium-11 is one of the most interesting ones because it has different decay modes where we can investigate this phenomenon, in particular, the beta delay proton emission. And it has a very long lifetime, which also favors that decay. But this is a very low branching ratio. That depends very much on the particle mass, as you can see here in this upper plot, if the pointer works, which is not the case. Okay, well, here. So this is the mass of this particle is similar to what could be the mass of neutrons or protons, and that influences very much the decay. And of course, if that happens in a system like a halo nuclei, it may happen that, for example, the neutron, which is not, it's kind of separated from the core, may decay into a dark matter particle with several conditions that we will see now. But in any case, just to introduce what it's one of the big questions here is that I said that one of the things that may happen is beryllium-11, which is a neutron-rich nucleus, may decay emitting the proton. This is the scenario that we are talking about, but this is very counterintuitive because it's a neutron-rich nucleus emitting protons. Normally, one would think that you get rid of the protons to get to the belly of stability, as you can see. Of course, beta decay is the predominant way of decay among all the exotic nuclei that decay, or not so exotic, and it's well studied. So, okay, so I think it makes sense to study the beta decay of beryllium-11 and see in which channels they are decaying. So there was a very first experiment done at CERN. It was an indirect way that tried to measure if the neutron from the beryllium-11 halo was decaying into something else that was not the neutron. And the idea was to implant beryllium-11 in a copper plate. So you implant it and it decays, we don't know how, into something, and the residue is what you analyze. And the residue is, they found that there was beryllium-10. So that happens because the decay was, the neutron was emitted and it was transformed into a proton there. The way this was done was not observing the proton, but observing the residue, as I said, using the AMS technique, which is once everything gets implanted, you bring it to the AMS, and then you analyze the sample and you figure out how many beryllium-10 is remaining there, okay? And they found that the branching ratio was extremely high, of the order of 10 to the -5. That's quite a lot compared to what it was hypothesized before, okay? That, well, there are several explanations for that. And one is that that neutron can decay, or the neutron decays into a proton into a resonance state on the daughter nucleus, which is boron-11, or there might be some unobserved resonance that we don't know. Okay. So since this experiment did not observe the protons, what we wanted to do is, okay, to plan an experiment to see the direct decay and observing the protons there. Okay, so of course, this has some implications for the dark matter, the hypothetical dark matter scenario that I presented there. But for us as a nuclear physicist, low energy nuclear physicist, this is very important because the distribution of the protons give you a lot of information regarding the structure of beryllium-11, but also beryllium boron-11. And we can extract the BGT and the strength of the decay, okay? So if we know that the previous experiment measured the combination of all decay branches going into beryllium-10, if we measure the proton with enough precision, which is very challenging because we are talking about branching ratios of 10 to the -5, well, we could see if there's any discrepancy between these two measurements to infer something regarding the possible exotic decay into a dark matter cluster, okay? So that's what we did. So, but before that, I'm going to show you what now we are entering into the experiment domain right now. So with all these ingredients in mind, now the question is, how do we measure this? One thing that I forgot to mention is that when these protons decay, they have very low energy because the Q value of the reaction has something like 200 keV. That's the maximum window that you have. That means that the maximum energy is 200 keV, and it's extremely challenging to detect 200 keV protons with good resolution, of course. So with that in mind, one of the first attempts is, of course, I don't think this was an attempt to measure the proton itself, but if you try to implant beryllium-11 into a silicon detector, which is the normal technique used for this type of experiments of beta decay, you see something like that. And what you see is that, sorry, not this, but what you see is that the beryllium-11 decays, okay, after beta decay into an excited state of boron-11 that has pretty high energy above the threshold emission of lithium plus alpha. So you later detect lithium plus alpha particle. And this is what you see here. You detect both at the same time. So you don't have this energy, but you have the sum energy of both particles. So this corresponds to this state going to the ground state of the lithium-7 plus alpha, but the lithium-7 can be excited too. And of course, the energy to excite the unit kinetic energy to excite the lithium-7, so it goes into a lower peak here. But if you really want to measure a decay channel where you emit a proton of 200 keV, you can clearly see that this is pretty much in the noise of the beta particles here. So that's almost impossible to do, or at least I don't know how to do it. Now, what if we change the topology of the target, and instead of a solid target, silicon target, we use a gas volume where we can implant the beryllium-11, and this gas volume, we put an electric field inside the gas volume, so the charged particles ionize the gas and produce ionization electrons that will drift with the electric field that we can detect in a path plane, segmented path plane. So we can reconstruct the tracks of the decaying particles inside the gas volume itself. And this is our detector, which is called an active target time projection chamber. In this case, was acting as a time projection chamber because the tracks are projected in time into the path plane as I explained here. So this is our prototype ATTPC detector, and it has a path plane, as I said before, of 10,000 paths. And you can see, for example, here an image of one of the particles decaying projected into that path plane there. And you can reconstruct the three-dimensional track knowing the position of each one of the paths and the time the electrons needed to drift from the interaction point to the path plane itself. So this is a cartoon that more or less explains what happens here when we implant the beryllium-11. So with this detector, we went to Triumph in Canada, okay, and we performed the experiment. This is also challenging, but I'm not going to spend a lot of time explaining the technical complications of doing this experiment. But in the experiment was performed. These are high efficiency detectors and with a pretty decent resolution. So they allowed for the reconstruction of the protons and alphas and lithium-7 tracks, which is what we expect from the decay of beryllium-11. And the detector was filled with helium and 10% of CO2, okay? And we implanted beryllium-11 at a very low energy of 390 keV per nucleon. Well, and this, we used the known branching ratio of the lithium-7 alpha to normalize the branching ratio of the protons if we were detecting them, okay? So the experiment was performed by pulsing a beam inside the TPC, okay? Wait a moment, 1 second, so the detector recovers itself, and then just open the data acquisition system and measure whatever it comes in, okay? So there's two forms to extract information from this, okay? The very first one is, let's measure in a like calorimetric mode everything that's implanted in the detector. That means that you sum all the energy that can be reconstructed from all the paths that have been fired in those events. And this is what you see. So essentially, you see all these peaks here. This is calibrated energy. We use a proton beam to calibrate also that. And what you see here is alpha particles, then a peak that contains alpha particles and lithium-7, but the alpha particle that comes with the lithium-7 that it's excited. And then on the low energy part, what you have literally is the excited lithium-7 and the protons that we are looking for. And as you can see, well, if one tries to find a resonance here, it's really very complicated unless you have a lot of statistics and some signature that there may be some resonance state here. So what we had to do in this case is, okay, this is, instead of measuring everything, what we do is let's analyze the shape of the tracks of all the particles that we have there, because every particle leaves a characteristic track inside the detector, depending on the gas itself, which is called the Bragg curve, and it's characteristic from every particle, okay? So, but to do this successfully, of course, well, sorry, I just want to show some examples of tracks. I want to also spoil the moment and tell you that this is a proton track, and I'll tell you later why. And these are reconstructed three-dimensional tracks from the projection in the particle, okay? So as you can see, these tracks, the Z projection is the total energy that the particle deposits in the detector itself. So as you can see, they have different patterns. This is probably an alpha. Depending, I'm not so sure what this is. This could be maybe a beta, low energy beta. I'm not so sure because it looks too straight, but it doesn't really matter. The thing is that you see that there's events or tracks that have different topology. But the big question is how the protons look like inside the detector, right? Because this is not trivial. The problem with this is that there's so many possibilities that if you really want to know that, well, you have to measure it. And that's what we did. We injected protons of exactly 180 keV inside the detector, and we measured the characteristic Bragg curve. The resolution of the detector is about 15 keV full width. And even though it doesn't look like very good, I can assure you that it's much better than conventional silicon detectors that you can use for this type of experiments. So that's one of the advantages of this. And of course, the efficiency too. Okay, I'm not going to explain about silicon detectors, but if anyone has any question, you can ask me. So once we have this curve, well, the analysis was literally doing a very simple chi-square fit to all the tracks that we have in the detector. Of course, the tracks come with an angle, so you have to project it in a way that you can use your reference curve, which was taken at 0 degrees, okay? So you project the angle back at 0 degrees, you reconstruct the energy loss, and then you try to fit. And as you can see, with the proton reference curve that was constructed with all the proton events that we have, we could find events, which are the squares one, that fit really well and didn't fit to lithium-7, neither to helium-4 that has more or less the same shape as lithium-7. Of course, the lithium-7 and helium-4 shapes were taken from the experimental data because we have a lot of them, right? And conversely, you can clearly see that the lithium-7 reference curve fits very well to those tracks that corresponds to lithium-7. So with that, we did this Chisquare analysis where we separated lithium-7, protons, and alphas, and we got rid of what we didn't want to use, and eventually we selected protons, and this is what we saw. And what we saw is that those protons that are decaying from the beryllium-11 halo decay, beta decay of the halo, the neutron, it's converted into a proton that it's emitted into one particular resonance on boron 11, a resonance that it's above the proton emission threshold. Otherwise, there wouldn't be any possibility of emitting proton itself, of course. And that kind of rule out the exotic scenario of having matter decays, except that the problem is that we measured the branching ratio, which was around 10 to the minus 5, was pretty consistent with the previous one, but our uncertainty is 30%, which means that if you are trying to figure out an effect of the 1%, this is obviously not very useful in that regard, but it's still useful for the theory to figure out that point, of course. But this is very important because what we found is a narrow resonance of around 10 keV in boron 11 at a citation energy of around 11.4 to 5 keV with a spin parity of 1/2. And this is what is connected to the quantum system view. This is like a resonance. It's like a coupling to the continuum of the boron 11 to that proton that is living above the emission threshold in a continuous state, but in a very narrow resonance. And this type of narrow resonances are characteristic that they exist in many systems. As I said before, they appear among many other nucleus. Okay. If instead of a narrow resonance, we will have a decay into a larger continuum, as we saw before, this branching ratio would be orders of magnitude much smaller. That's of course characterized by theories. Of course, as it happens with this type of results that are not easy to measure, the experiment is difficult. Well, there was answer from theory that tried to reproduce the result. At the very beginning, there was some positive feedback regarding, well, okay, there was the theory is in favor of about the formation of the resonance, and you can see here. And this is, for example, different nucleus that have several states with narrow resonances too. And boron 11 is here, and well, as you can see, there was some nice work there done to validate the existence of the resonance. I'm not talking about the branching ratio, but there was also some other models, like for example, some model calculations that were against this result, especially because of the branching ratio doesn't fit with the expected resonance there. Okay. Of course, there was a second attempt. There was a lot of criticism regarding the analysis itself, the interpretation, well, everything, of course, especially regarding the identification of the particle. I'm not going to show it here because I think I'm running out of time, but we reanalyzed the data with a more complete set of energy loss curves and other type of analysis that we are about to publish it too, by the way, and we found more or less the same result. So this is kind of ruled out within our analysis. And also, well, the BGT that we gave was quite high, but that was within our error, which was pretty low. After that, well, I don't know if it was after or just 1 year later, I don't remember exactly, there was another attempt to measure the same branching ratio using another technique, the same technique as explained before with the EMS, implanting beryllium-11 into the foil, bringing it to the EMS. And these are the results. And as you can see, the uncertainty is very large, because for different samples they used in the experiment, they obtained very different results from the branching ratio. And as you can see, this is our value there. And for some reason that still do not understand, they adopted this lower upper limit, if you will, which is kind of like 1 order of magnitude lower than ours. What this means? This means that the branching ratio question is still open, and it's still open in particular because theory is still not happy about it. I'll show you later, because that was a latest result that was published in arXiv a couple of days ago. But what's our mission as physicists? So we want to validate this. So one way would be to redo the experiment, okay, with much better conditions. That this is something that we are trying to do at some point, and we are designing a new type of detector with much better capabilities than the ATTPC. But of course, this takes time because we need to test it, and we have submitted a proposal in Triumph to do it. But one thing you can do is, okay, if there's a resonance there, it can be formed when you bombard protons, protons or beryllium-10 with protons, but at very low energy, because the protons have to be emitted with very low energy. So that's what we did. We proposed an experiment that we conducted at EFRI this summer, actually in July, okay? And as you can see, the setup is very simple. So in our proposal, this is, okay, the resonance that we are looking for coming from the beta decay, but it's not affected, of course, by the nuclear potential, should have this shape if we do the scattering reaction on beryllium-10. This shape comes from the fact that it's very low energy, so it couples to the Coulomb scattering there. So you have interference of the resonance, okay? That's a very well known, okay? And of course, the shape of the resonance changes depending on which angle you measure it. So since we expect that L equals 0 resonance, that maximum at 180 degrees. So our experiment was designed to measure protons coming from the scattering of a beryllium-10 beam on a proton target, okay, at forward angle. The setup is really very simple, and we did this experiment with 2 channels, literally, 2 electronic channels, 3, because there were 3 detectors. So what we used was a microchannel plate detector that has the target of the microchannel plate. I don't know if you are familiar, but the microchannel plate is a very fast detector that takes electrons and amplifies them. So the electrons, let's see if this works. The electrons were coming from sputtering in the foil. There was a luminized side. This side of the target was illuminized. So that was giving us a signal, because this was deflected with magnets into the microchannel plate. That was giving us the timing signal to measure time of flight of the protons that were scattered inside the CH2 target, okay? So for those of you that are not familiar with resonant scattering techniques, what you do is literally stop the beryllium-10 beam inside the target. So you scan the whole energies in center of mass where the resonance is, okay? So that's what we did. The beam never went through the target in this experiment. So we were only seeing protons or something else. And actually there's something else, I'll show you. So I designed the whole setup. It was easy to mount, and we performed the experiment, and this is what we saw, okay? So as you can see here, we see we used from the silicon detector. This is the central one. The side one was not working very well, unfortunately. But this is the total energy without calibration and time of flight. I don't have here the time of flight spectrum, but since these are very low energy particles, both protons and alpha have very different time of flight, as you can see here. So we had a self-calibration source, if you allow me to say that, and actually the point is that the chamber that has some contamination from the source that we use, but still useful because those are peaks from the thorium source that were very useful to calibrate the system. And this is the time of flight line of alpha particles, and these are the protons. So as you can see, we were at the very, very limit of the threshold there, okay? And one thing I want to remark is that this experiment was performed with between 100 and 1,000 particles per second, because the quality of the beam was not great in that regard, because this was kind of like a reaccelerated beryllium-10 source. It was not even produced by fragmentation or reaccelerated. It was a beryllium-10 source that was developed for this experiment in particular. So that was very challenging. Good news is that we have been granted more beam time to continue with the experiment, not because of the resonance itself, but some effect that we'll see. We'll also be now. And this is what Ulita is. So this is the spectrum that we measure after calibration. We use protons to calibrate the detectors, okay? So if there's no resonance or if there's another effect there, obviously in the absence of resonance, what we'd see a Coulomb or Rutherford scattering, okay? So this is the curve. This is preliminary, and by the way, we are preparing a publication. So this is the Rutherford scattering, theoretical line of the Rutherford scattering, okay? But we can clearly see a dip in the excitation functions here. And it really matches very well with the position of the resonance that we observe. Of course, this was fitted, I'll explain you how this was fitted, but it matches very well with the resonance. But what does not match very well is the width of the resonance itself. When we proposed the experiment, we assumed that 100% of the width was going to the proton emission, but it turns out that the shape does not correspond to what would be for 100%. So we had to take into account that there's also an width for the emission of alpha particles, which means that the system at that level in particular also decays by emission of lithium-7 and alpha. And that's what we want to do. There's some interesting things here, as you can see, that because of the properties of the resonance itself, the interference does not make the Rutherford scattering go back to what it would be. And this is a thing that it's quite new, and we perform calculations not only with two different R matrix programs, but also trying to build the resonance by using optical potential. And I think that this is a real effect that could be explained because of the penetrability of the particular channel itself. Now, well, I put there the other spectrum here. If okay, you can see the beta decay to compare. Okay. So what happens with that alpha channel? That alpha channel, of course, the alpha channel is not subject to the potential scattering. So it would be the typical textbook bright beam resonance that would be affected for that. So what we want to do is, because of the cross sections were very small for the alpha particle itself, we will repeat the experiment and have more statistics to give a more precise value of both width. So this is like more for the students, let's say like that. It's that this is how the resonances look like if you have the proton channel, which is what we saw, but the alpha channel would be the one below that has much lower cross section, because obviously the Rutherford cross section is much larger here. So we'll try to identify this, and because I didn't show it here, but we see the alpha particles, so we just need more statistics, and that's what we'll try to do. And of course, this doesn't solve the problem of the branching ratio itself, right? Because this is a different reaction. But recently there was a paper published again by the same team that argued that the resonance was there, and now they are arguing that one of the things that they cannot match is the width of the resonance and the branching ratio. So I don't know where this is going to be published or it will be accepted or not. But as you can see within their calculations, this is our limit for the branching ratio, and this is what they predict depending on the energy of the proton. So as you can see, there's still some nice tension between the experiment theory and other experiments here. But the only thing that we can do is just measure again and better, of course. So these are my conclusions. I don't know if, okay, I'm on time. So as I show you, this nuclei are particularly interesting system that can be seen as open quantum systems, where there are some properties that appear there, exotic properties because of this interplay. Okay. I also show you that among all the systems that we have there, beryllium 11 is a special case because it emits protons. Just to conclude about the dark sector emission part is that, well, we do not believe very much that that exotic channel may exist, but I have to say that this is still quite a lot of undergoing efforts to try to measure this type of decay, not only in beryllium 11, but other systems. So what we suggest is that this decay in particular goes through a resonance, narrow resonance above the proton emission threshold in boron 11, okay, which is not so exotic, but still very interesting. And as I told you, well, the large branching ratio discussion is still open there. And of course, I think it's encouraging not only for us, but for everyone that is interested in this, that one has to really push the detection technology to make this experience better. And I think that it's worth. So, and that's pretty much. And thank you very, very much for your attention.
Thank you.